So shall we start or wait? Okay, may I introduce Lucia Borgio? I know Lucia Borgio since long time. I just want to say to her one thing that happened. Do you remember, Lucia, how many times we came to the Victoria Albert Museum to study the luster decoration by Mastro Giorgio? Many
yes.
times.
Yes.
Once we were in France, it was raining, cats and dogs. I was swearing, saying, why do I have to go to the bloody Victoria Museum to study something that was decorated in Gubbio, 20 kilometers from Perugia? That is life. Now the microphone is yours, Lucia.
Thank you. Good morning, everyone. It's a real pleasure to be here and be reunited with many of the cultural heritage Italian diaspora. It doesn't happen very often. For those of you who don't know the institution I work for, the Victoria Albert Museum, it is one of the few institutions in the UK to have a dedicated team of scientists in-house working on collection-related issues, but also addressing research questions and providing access and support to external partners and requesters. The lab is relatively small, but it's very equipment dense, and it's intensively used. Here on the left, you can see a list of all the major scientific instruments that we have, and many of them were upgraded recently thanks to a UKRI grant 3 years ago. And one of the greatest strengths that we have, and it was touched on earlier today, this morning, by the other speakers, is that there is such a close collaboration between conservators, curators, and scientists, which is a lot more pervasive than I have witnessed anywhere else, and we really treasure it. It's what I call the magic triangle, which later on transforms. I will show you how it transforms into a magic polygon, possibly, or with many more sides than 3. Historically, a lot of the work that we do is routine, or what is normally called routine, responding to queries from conservators and curators, to enable the V&A's public programs, so exhibitions and loans and display, but also collection care and scholarship issues. And at the same time, though, we do collaborate with other collections and researchers from other institutions to advance the field of heritage science and developing new methodologies and making new discoveries. What you see on the screen is just some examples from the last 18 months, but there is so much more happening at the same time. I just didn't have enough space on the slide, unless I wanted to have very tiny, tiny, tiny photos. The fact that much of what we do can be described as routine, in inverted commas, does not preclude discoveries and groundbreaking surprises. Many of the most recent discoveries at the V&A, such as the ones that you see on the screen at the moment, happened during the course of what has started as a routine analytical campaign. What's the secret ingredients behind these discoveries? Is not state-of-the-art equipment, is not new methodologies, is not money, although obviously all 3 counts quite a lot. I think it's the attitude of the scientists. It's the curiosity that we have, mixed with a hefty dose of skepticism. And I always tell my students never to trust themselves, always question everything, never assume anything, do not have any preconceptions, because you need to start from a clean slate. But it's also the humility of not thinking that we are the experts and we have all the answers, although many times, most of the times, we actually are the experts and we do have many of the answers, but don't start from that position from the very beginning. And last but not least, hunger. Hunger for new things, at least that's true for me. heritage science should never become a boring day job, 9 to 5. This way you can keep your outlook fresh and start every project with a clean slate, without assumptions, ready to be surprised and ready to enjoy the process. As I implied earlier, the separation between collection care and official proper research is less marked than you would expect. And today I will touch on two projects, two examples that did not start as bona fide projects in terms of research, but stem from our routine care collection activities. And please bear in mind that this is unpublished, ongoing work, so do not reuse any of the images or concepts that you see on the screen until it's been published, because obviously we wouldn't be, or the powers that be at the V&A wouldn't be very happy. The first set of objects I'm going to discuss here is anything but routine. It's the V&A Foster Codices, which is Leonardo da Vinci's own notebooks. They're very small, as you can tell from the image of me with them. And they contain handwritten notes, like in this page, or architectural and technical drawings, as well as preparatory sketches for Leonardo's own paintings. And the reason why we were asked to look at the codices was to understand the materials that Leonardo used to write and draw, and inform conservation and display decisions. And in particular, we needed to qualify the risks of lending the manuscripts for an exhibition abroad. So you see, it's a very practical reason usually behind the questions that we are asked. One of the risks depends on the presence of iron gall inks, which, as you well know, can corrode the page and eventually destroy the page itself. Didn't happen with Leonardo Codices, I swear. And we also wanted to characterize the sanguigna, which is the chalky pencil or pastel that Leonardo used on extensively on all the codices, and compare the different types of writings, because there is something that is obviously written by him, even if it's done with different inks, but there are other handwritten notes that we suspect they are not his and were added at some point during the codices histories. And then we would be able to discuss with curators, conservators, to decide if any treatment is needed, to provide guidance on handling and display, and make comparisons with other notebooks and manuscripts elsewhere. This is our non-invasive analytical protocol, which included infrared reflectography to observe differences in the writing materials absorption in the infrared, high-resolution digital microscopy to highlight details, scanning XRF to define the distribution of elements on the pages, and finally Raman microscopy to confirm the molecular composition of the writing materials. And one of the things that we were able to confirm indirectly is that Leonardo often took notes using sanguigna while on the move, and then only the notes worth keeping would be retraced with ink once Leonardo was back at his desk. And you can see this in the photo on the right-hand side, because there is an imperfect overlapping between the sanguigna and the ink. Excuse me. The analysis by Raman microscopy of this page confirmed that hematite is the main component of the sanguigna, and iron gall ink is the main component of the ink. If we look at the XRF analysis, the XRF mapping, it did give us a clear visual indication of this, because the iron map matches both the sanguigna. Thank you. Both the sanguigna and the inks, and visually there is the added complication of the fact that the XRF map shows everything that is present on both sides of the page. So you see the map of iron that comes from both the verso and the recto of the page, which, if you want to get a nice clean image, makes life a bit difficult. And then, as I mentioned earlier, there were different types of inks on the codices, and it would be very tempting to try and identify them by eye and say, oh, the black ones are carbon-based ones and the brown ones are iron gall inks. Obviously, we know better than that, and in this case, we had to test them all, and they are all mixtures containing iron gold links, with the exception of the one on the top right of the screen, the yellower ink, for which I was only able to identify the impurities. So by Raman, I could identify carbon black, hematite, and orpiment. And just by the look of the inks under the microscope, I could tell that there was probably a very diluted version of iron gold ink and an hydrated iron oxide of an amorphous type. But obviously, I couldn't get a Raman spectrum, so it is still all based on experience and expertise and good old guesswork. On some of the pages, the infrared reflectography experiments revealed something unexpected. As a general rule, carbon blacks remain visible in the infrared. Iron gold becomes transparent in the infrared. Occasionally, we have something in between, which probably indicates that iron gold link was mixed with other things that makes it still visible in the infrared. And there is an intriguing piece of evidence. If you look at the bottom right of the infrared image on this slide, you can see that the iron gold link is a lot more visible on the right of the paragraph than it is to the left. And remember that Leonardo was writing with his left hand, right to left. So to read it, we have to use mirrors now. And obviously, when he put his nib on the ink and then started writing, there was something in the rheology of the ink that allowed the infrared visible elements to be retained at the beginning and then not to be present anymore at the end of the line. And again, it just gives you an inkling about the way he used to actually physically write things. This is ongoing work, so we are not drawing any conclusions. There are still experiments to be done, but I thought it would be something that you haven't seen anywhere else because it hasn't been published yet. So to sum it all up for the first case, so for the Leonardo codices, what we are doing is allowing to shed light on the history of the codices, for example, the way they may have been put together. They help in their authentication, for example, by identifying original materials, later additions, but also past conservation treatments, and to address conservation concerns, specifically identify the risk of lending the manuscripts for an exhibition, monitoring the degree of degradation of iron gold links, and advise on the sensitivity of materials. And this is my second example, which many of you are probably already aware of, at least the beginning of it. This study relates to indigenous American lacquer, which is something that I started working on relatively recently, but is really a gift that keeps on giving. What is it? There are different types. The most famous one is probably Barniz de Pasto, which is obtained from the buds of a plant that grows mostly in the Andes in South America. But there is also Mexican lacquer, which is made of chia oil combined with an insect fat known as aje. And then many, many other types of regional lacquers that are from all different regions in Latin America. What is common in all these objects is the glossy and durable finish they all exhibit, and you have a few examples here. Some of you may have already heard of this. This table cabinet came into the V&A in 2015 and was routinely analyzed just as any high-profile object that enters the collections. And the first discovery was that the white pigment used ubiquitously here was calomel, which I promptly rechristened mercury white because it was the very first documented occurrence of it as an artist pigment. So we have lead white, we have calcium-based whites, and I christened it mercury white. And the first surprise came, the second surprise came when we x-rayed the cabinet. You can see here the lid, what you see with your own eyes, and this is the x-radiography, which has nothing to do with what your eyes see. There is a skeleton in the center. And so we used micro-CT at the Natural History Museum first, and then mapping XRF at the National Gallery, who generously gave us access to the equipment before we bought our own. Yay. And this map shows all the areas on the lids where mercury is present, outlining what must have been the bulk of the original decorative scheme made with mercury white. And with other analysis that I did, I could confirm that what we see is a 20th century repaint, and after some sleuthing, I confirmed that the pigments must have been applied after 1958, so it's something quite recent. To cut a long story short, 8 years after discovering the presence of the hidden skeleton, it was just 2 weeks ago that my colleague Dana Melker started removing the late 20th century paint to reveal what was the original scheme. And you can see here on the left, and to my great delight, I was actually allowed to remove some of the paint myself, so I donned the lab coat and was allowed to be a conservator for a few seconds under Dana's guidance. And it was really something very nice from a personal perspective. And what you can see is that the removal of the 20th century overpaint reveals so many additional details and colors we had not expected at all, because they are all organic, so they don't show up in the X-ray maps, the XRF maps. And there is a variety of pinks and mauves which cannot be seen anywhere on the cabinet because they have actually faded. So that brings a lot of implicit issues about how do we exhibit this, how do we display, how do we make sure that what has remained untouched continues to remain untouched. Going back to American lacquer in general, because I'm aware that I'm running out of time. As a result of our research, we developed an international network and fostered new knowledge exchanges about these objects. We overcame both geographical and language barriers because we organized our first international bilingual gathering dedicated solely to indigenous American coatings. Speakers came from all over the world, and we had so many different people gathered together with so many different backgrounds. We had scientists, conservators, curators, and art historians, which is normal in a museum setting, but we also have social anthropologists and designers and makers and jewelers and so on. So this is, instead of having a magic triangle, we have a magic octagon. And as a result, we are all now looking for items that are made of indigenous American lacquer in our collections, but we have not recognized as such so far, and we have helped to identify one at the British Museum and one at the National Trust. And this is my last slide. You will be very happy to know. I know, but I get anxious. So what to take away from this is that, I know to you this is all very boring and very obvious, but to people who are not in a museum setting, this may not necessarily be obvious. The border between routine collection care and research is more porous than expected. And you really need to continue to be curious and open-minded in order to keep that fresh outlook on heritage science. And the magic triangle or polygon really works when you really put some effort in it. And just by looking at the program for today, so it doesn't have anything to do with the V&A or with my work there, the fact that there are so many of us doing this work is a testament to the quality of Italian education. And I'm talking from primary school onwards, not only just university, in the 70s, the 80s, and the 90s, and in the case of some of the speakers today, even the noughties, the 2000s. So well done, Italy, because you have spawned a lot of us, and we are kind of secretly and silently invading the world. And a few acknowledgements, Dana and Valentina at the V&A for their work on the Barniz de Pasto and Leonardo, respectively. Marta, who spoke earlier, and David Peggy at the National Gallery, because one of the maps that I showed today was actually taken by them. And I did mention them before, but I didn't show any of those results. The Natural History Museum, of course, because they helped us with the micro-CT of our cabinet. And all of you for your attention.
Thank you, Lucia, for your comment on Italian education. Also, you used a few times the word amusement, joy to work. And I can give my personal experience, how it is important to work seriously with enjoyment. I am now involved in a very crazy project, crazy from my age. We are, we are giving to 9 Italian contemporary artists Egyptian blue to make their artistic procedure with these new materials. And we are planning 24 exhibitions in the next 3 years, 12 in Italy, the other all over the world, States, Egypt, China, and so on. So I was trying to find a sponsorship, and I had an important meeting with any top-level management. When they asked me, why are you enterprising this venture, this project, I say, because we want to work with amusement and joy. And that was the working word. They appreciate very much the fact that we working with amusement and very seriously. And they gave the sponsorship. So it's very important to have this attitude towards our job. Thank you again, Lucia.
Thank you.
Now we pass to through 2 remote presentations. Until now, the remote presentation was very, very good indeed. I must say that I am a little contrary to remote presentations, but I am astonished how it's working in this. And my compliments to the technicians that are doing such a good job. Now, Eleonora Pellizzi, Gianluca Pastorelli from the Copenhagen State Museum for Kunst will have the microphone. Gianluca, it's your time to talk.
Yes, thank you very much, Professor. I hope you can all hear me.
Yes, very well.
Perfect. And,
unfortunately.
I will try to share my presentation and hopefully also put it full screen. All right. So today I'm going to talk about a bit how artificial intelligence and specifically machine learning are revolutionizing the field of heritage science. And I will focus on a few case studies related to the Danish painter Willem Hanassai. And I will structure my presentation in 3 sections. I will talk a little bit about my personal background. I will show then the case studies I just mentioned, and I will conclude with a few comments about the future of heritage science. So, regarding my personal background, I am currently a senior heritage scientist at the National Gallery of Denmark, or SMK. But my path, the path to get to this position has been extremely convoluted. I would say that it's not a textbook example, but everything started with a master's degree in natural sciences, specializing in natural conservation, so a very different type of conservation. But this gave me a general scientific knowledge that I could apply on my first job as an environmental chemist at a local environmental agency. I was basically the guy who makes sure that the water coming out of your kitchen tap is drinkable. But then I wondered whether the analytical equipment that I was doing for that job could also be applied in other contexts, such as the study of cultural heritage. And this led me to pursue a postgraduate degree in archaeology and archaeometry, where I could indeed apply those scientific methods to the study of cultural heritage. And after that, I worked for a while as a geoarchaeologist, where I finally had real contact with ancient artifacts, and especially with a material that I find most fascinating on Earth, which is amber. I could work on archaeological artifacts made of amber. And just because people often ask me this question, I'm going to answer it right away. No, I never managed to extract dinosaur DNA from amber, but I could see that a material like that is very prone to degradation. So this created some interest in me regarding the topic of conservation of cultural heritage. And this made me pursue a PhD in conservation science. I was enrolled at the University of Bologna, but I carried out most of my work in Denmark. And finally, I could become a heritage scientist, and I had the opportunity to work in different prestigious institutions around the world, including universities and museums, and focusing my research on characterization of artists' materials. And I guess Francesca can probably recognize in the bottom corner one of the artworks we worked together some years ago. But that's enough about me. Let's talk about Willem Hammershøi. Hammershøi is a Danish painter who was active between the end of the 19th century and the beginning of the 20th century. And there is an international interest that is growing in this artist. At the same time, his painting techniques and material choices are relatively unexplored. So that's why we created this project, the Willem Hammershøi Digital Archive, which aims at shedding light on his working methods, and including the use of very specific pigments. In this project, we result in an open access online archive, which will hopefully advance art historical research and authenticity assessment, and also conservation of artworks by Hammershøi through all the technical data that we are producing. And talking about applications of machine learning to the study of artworks by Hammershøi, this is actually an example, and this work has been published recently on X-ray spectrometry. We worked on this portrait. It's a portrait of another artist, incidentally, Jens Ferdinand Willumsen, but it was made by Hammershøi. And we work a lot with X-ray spectroscopy, mostly macro XRF. And the usual way to work with this technique is to produce these single element distribution maps and to find correlations between the different elements in order to identify pigments. But we tried a different approach. We used a machine learning technique based on neural network that is called the self-organizing maps, which can produce, among other types of plots, these heat maps that are related to single elements, but allow us to look at the presence of these elements in a different way. For example, we can see very clearly the similarity between the maps of phosphorus and calcium, suggesting the use of bone black in the paint layer of this painting. But also, if you work with XRF, you know how challenging it is to distinguish the signals from barium and titanium. Well, these heat maps actually can show that the signal from barium is actually extremely noisy, while the one from titanium is very localized, indicating the use of titanium white for retouching. And again, the correlation between cobalt and nickel, that it is suggested by the maps, the XRF maps. Actually, this correlation is absent in these heat maps. And we can see that only cobalt is actually present, while the presence of nickel is basically an artifact. We can then try to use further techniques such as hierarchical cluster analysis to create groups of elements that are related to specific materials used in the paint layer, and we can plot these clusters, and we can also separate them and inspect their individual elemental compositions. And I don't have the time to go to the details, but it's interesting to see in cluster 7, for example, which is very rich in cobalt, and this cluster is associated exclusively with the eyes of the figure in the portrait. We try to use these techniques also not only with XRF, but also with SEM EDX analysis. We collect samples from the tucking edges of all the Hammershøi paintings that come to our laboratory. And we tried to explore the composition of all these samples in order to identify the types of ground materials that were used by Hammershøi. And this is what we obtained. We could identify 5 main types of ground layers, and we could plot them versus the year of production of the paintings that we analyzed. And we can see that most of the paintings have been produced with ground layers composed of mostly lead white or a combination of lead white and calcium carbonate. But there are a few outliers, such as these 2 paintings, mostly composed, which have a ground layer mostly composed of calcium carbonate. And these paintings were produced by Hammershøi when he wasn't in Denmark. The portrait was produced when he was in France, and the church interior when he was in Italy. So during those times, he was exposed to different materials, and these drove a little bit his choices. And then there is this unique painting that contains a ground made of an iron-based earth. And the time when he produced this painting, he was still a student. So it's something very different because it's not really an expression of his art, but it was basically a school assignment. Changing topic, we don't work, of course, only with XRF. We work with other techniques, everything ranging from UV reflectance spectroscopy to visible spectroscopy, near-infrared and mid-infrared spectroscopy. And very often, when we acquire spectra using these techniques, these spectra are mixed. They contain reflectance bands that originate from multiple materials present in the artworks. So the problem is to identify the components that make up these mixed spectra and try to quantify their contribution to the acquired spectra. And the steps for what we call spectral mixing are basically 2. First, we need to identify the reference spectra, or enmenders, as they are known in the field of hyperspectral imaging, that contribute to the mixture, and to compute the mixing fraction for each enmender. Now, I really don't have the time to describe all the techniques that have been successfully used for this task, but we focused on one technique that is very useful for single point measurements, so not hyperspectral imaging, but single measurement. And this technique is non-negative least squares. Based on this technique, we developed a workflow, which was presented recently at the IRAG 15 conference in Tokyo, Japan. And again, I don't have the time to go into the nuts and bolts of this method that we developed, but there are different steps, such as the concatenation of different spectra that are acquired with different techniques in order to create these broad spectra that contain all the information that we might need, and then the unmixing process based on non-negative least square, and the identification of those components using an ensemble of supervised machine learning techniques. We originally developed this technique for identifying cobalt pigments, but now we use it for all the different pigments that we have included in our database. And some algorithms work better than others, but in general, we can reach a fairly good accuracy. We don't use this technique very often for Hammershøi because he used mostly inorganic pigments, and we make extensive use of XRF. But we try to play a little bit with it, and specifically on this example, where the foliage, the green foliage in this landscape was produced actually with a mixture of cadmium yellow and cobalt blue, and this was confirmed indeed by XRF spectroscopy. To conclude, because I see that time is running out, we also try to work a little bit on the correlation between crack morphology and ground materials. Especially, we did this working on another Danish painter who is Jens Juul, and this is an unpublished work. But we try to classify the cracks that are the crack patterns that are developing on the surface of many paintings by these artists. And using principal component analysis, we could group these crack patterns into 4 distinct categories. We also used the SOM-HSA method that I described previously to classify the different ground layer materials, and we could identify 4 different types of ground materials. And we tried to see if there is a correlation between those 4 crack patterns categories and these 4 ground layer types. It's not perfect, but there is a fairly good correlation. So the goal is to develop an image classification algorithm based on supervised machine learning and convolutional neural network in order to automatically classify crack patterns on the surface of the painting and therefore infer the composition of a ground layer. When we came across this painting by Hammershøi that developed these cracks on its surface, and this is a pattern that the conservators call alligatoring, which I find amusing, but also very spot on. We tried to see if there was a correlation, according to the model that we developed for Jens Juul, between the ground material and this specific crack pattern. We can see that the ground is mostly composed of lead white, and according to that model, there is no match. So we assumed that there is another material in the paint layer that is actually creating these cracks. And we sampled, we collected 3 samples. It's something that we don't do very often, but we collected samples from the paint layer and we analyzed them with ATR, FTIR, and we could indeed identify asphalt or bitumen, which is a hydrocarbon-based pigment that indeed on the long term is prone to the production of these specific crack patterns on the surface of the paintings. So to conclude, what is the future of heritage science based on what I presented? Why artificial intelligence-driven methods are important? Well, for different reasons. Scientific methods are becoming more and more efficient. They can collect a very large volume of data very quickly. So it's necessary to use advanced data mining techniques to find meaningful patterns and trends in that extensive data. And also sometimes researchers don't have the opportunity to use multiple complementary techniques to identify materials accurately, especially when these materials are mixed. So it's important to develop methods, the mixing methods that can work with limited data, and they can improve the characterization of materials. And also, very often it's challenging to decide whether or not to collect samples. So to have advanced models that can predict certain type of results can help researchers in making better decisions regarding the collection of samples. So I want to thank you for your attention, and especially I could thank 100 people, but I really would like to thank specifically some of the forward-thinking people who have helped me to shape my career, and I am very grateful to them. And again, thank you all for your attention.
Any comments, questions? No? We thanks again Gianluca, and we pass to the next speaker, Eleonora Pellici. In the program was a remote participation, but with great joy, now she appears in presence. From Parigi to Rome, the microphone is to Eleonora.
Thank you so much, Antonio. Yes, actually, the BNF proposed me to come, so I couldn't say no.
Yeah. Always Rome deserves a mess, like Paris.
Yes. Thank you so much, and thank you to the organization for inviting me. I'm Eleonora Pellici, and I'm working at the BNF, so at the National Library of France. And I want to share with you today recent study on the conservation of rubbers in contemporary and modern art collection. But before that, so few words on my backgrounds. I studied at University of Turin, so I had a bachelor and a master degrees from the University of Turin that allowed me to have a really good background on materials and their degradation. And here you have just two examples of work of arts that I work on. So a manuscript and a funeral mask of the Egyptian Museum. And as been already told today, I'm really grateful to the Italian education for giving me a very solid scientific background and to a very early class in the university with art historians as well and restorers. After my degree, I went to Paris and I started working at the Research Center for Conservation that is in the Natural Museum of Paris, where I worked really with problems and issues coming from conservators' problems. First on the Haringel-Hinks issues, and then I made my PhD on the conservation of polyurethane foams that was founded by a European project that was called POPART. And so there I really started to work on issues really related on conservation problems. And then after my PhD, I had the opportunity to have a postdoctoral fellowship in the Center of Atomic Energy in France, where I studied the degradation of synthetic materials, so of plastics, under ionizing radiations. So I really learned a lot about the analytical techniques. So I really thanks the Atomic Energy Center. And what I learned as well was the importance to really share in a very clear way with the with all the people that are working on a project, and just to make the exchanges as clear as possible. But then I really missed the cultural heritage field, and I had the great opportunity to join the BNF in 2016. And there, it was really a good opportunity for me, because at the National Library, I really can combine all the experience that I had before on the writing materials, on manuscripts, and also on all the experience that I had on synthetic materials. And here I put a very good example of that, because this is a printed book that is conserved on a polystyrene coffin that is that had a box of cellulose acetate. So it combines really a lot of different problems in one. And here you can see again the three field scheme with scientists, curators, and conservators. So all the experience that I had really lead to me to learn how to work well in between scientists, curator, and conservators. And what helped me as well was to work with formation center for conservators in France, so like the Institut National du Patrimoine and Beaux-Arts in Tours. So there I work really in the formation for conservators. What is really nice in the BNF is that you have scientists, curators, and conservators working together in the same institution. And so this is a real advantages for conservation science. And what I think as well is that, at least at the BNF, the scientific research had to really answer to conservation and curator problems. So this is the reason why I will talk and share with you this project about rubber, where we started to really collaborate with conservator working at the Centre Pompidou. So how this project started, we realized that we have very similar problems in the collections. So you can see here on the left and on the right 2 works of art of the Centre Pompidou. So the plus and minus box of Robert Morris and the plinths from Richard Serra. And at the BNF, so at the Centre Pompidou, you have a lot of obviously modern and contemporary materials and a lot of rubbers of many different kinds. And on the BNF, we have a very big collection of technical devices that are conserved to reproduce audio and video supports. And in this historical collection, you have a lot of rubbers. So we found it to have very similar problem of conservation. And here you can see 3 images of the typical degradation that you can have on rubbers materials. So we decided to work together, but at the beginning we have to define clearly what were the objective of this collaboration. So what we wanted to do, first of all, we had to be able to identify clearly the nature of the rubbers in the collection, and we realized that we were not able to do that. And why we wanted to identify the nature of the rubbers was to better understand the degradation that we observe in the collection, and at the end with the aim to develop conservation treatments. So we started with the first question, so how we can identify clearly these materials, and we looked for foundings because it was absolutely necessary to perform this research. So we had found this from a foundation, French foundation, that is the Fondation des Sciences du Patrimoine, from the French Ministry of Culture, and as well for a foundation of the Michelin company that helped us so much in this project, because they really have a lot of knowledge, obviously, about rubbers. So what rubbers are? Actually, rubbers in the pre-Columbian Mesoamerican civilization, they already know really well how to produce an elastic materials from the latex that you can get out of EVA trees. But in the modern time, it was from 1839 that in Europe it was rediscovered, the vulcanization of the rubbers by Mr. Goodyear. And at the beginning of the 20th century, we have different kind of new family of rubbers that appears, that were now synthetic materials. So you start to have natural rubbers and then polyisoprene synthetic rubbers with a lot of other families of rubbers like the APGM, SBR, NBR, etc. And what is important to know is that when you have a synthetic material like an elastomer, you always have a polymer and a lot of additives. So this complexified quite a lot the identification. We also decide to work with other scientific laboratories. So we work with the CRCP in Marseille and the C2RMF in Paris joined the project as well. And they work with us on the scientific part of the project that is called ESPION, so it's elastomers identification by pyrolysis GCMS in museum collection. And the idea was really to develop an analytical methodology in these laboratories, so that we can share the data and we can reproduce the methodology on the 3 labs. And we wanted to test this methodology on the collection of the Centre Pompidou. So what we started with the constitution of a reference database. So we collect a lot of reference materials, so partially from the Michelin company, and from chemical suppliers as well. And we analyze all these different elastomers to create a reference database. And we use a multi-step process with the pyrolysis GCMS. So what we have done, we take the sample and we heat it at 200 degrees, so we can analyze only the additives of the samples. It's this what you can see here in the pink chromatograms. And then the same sample, we heat it at 600 degrees to really have the signature of the polymers. And we have done that with all the reference that we had. And then the idea was to do exactly the same on the samples from the works of art. So what kind of data we have? We had, here you can see two kinds of chromatograms of two reference. So on the upper part you have the styrene butadiene rubber, and on the lower part you have the butadiene rubber. And what we had, the information that we can have were to see some characteristic markers of families of polymers that are so common to different kind of elastomers. And then for some specific case, we have really discriminant markers of one kind of elastomers. And we collect all this information on a database to help us in the identification. So I just show you very rapidly how this works. So this is an example on one of the sample of work of art from Gilles Touillard. This is the interface of the database, and in this part you can import the data, the raw data that are constituted by the 10 major ion of the mass spectra up to 25 major peak on the chromatogram. And when you put your raw data in the interface, you can have an immediate result with the best comparison with all the elastomer of the database that we collected before. So for this special case, we had polychloroprene. So we analyzed last year 265 samples from the collection of the Centre Pompidou. And we have seen that they have a lot of natural rubbers or polyisoprene synthetic rubbers, because we realized that we cannot differentiate really the natural rubber from the synthetic rubbers. And all these data were analyzed also by the conservators of the museum to see if we can see a connection between the nature of the polymers and the degradation that we observed. And so all this data analysis is still ongoing, but we can see that a lot of the objects that have conservation problems and degradation apparent are almost natural rubber and polyisoprene. What surprised us a little bit was that even if we construct our database on new materials, so not degraded materials, we had a really few amount of sample that we were not able to identify. So this was quite good for us. And before concluding, I just spent a few words on the age of the samples. So here you have the picture of some sample identified as natural rubbers of different ages. And what we can see in the analysis, we can see that in the three recent samples have a very similar signatures, and we can clearly identify the characteristic markers for polyisoprene. When the rubber is aged, the signatures start to change a little bit. So you can always see the characteristic markers, but you start to see also different kind of molecules that are modified terpenes that are probably due to the degradation of the isoprene dimers. And so this is a big project that we started, and it will not end in 2 years, so we will still keep going to work on it. And now what we would like to do is to have a better understanding of the degradation of these materials, especially natural rubber, and we would like to reproduce in the laboratory some samples for conservators so that they can make some restoration tests on samples that are representative of what we see in the collection. So this is the phase that it's ongoing now at the laboratory. And I just want to thank you so much, all the people that work with me in this project, and especially Caroline Bouvier that spent 2 years working on the project as a postdoctoral fellow, and that he's going to work with the Risk Museum next year. And special thanks also to Isabelle Cuoco, that he's the conservator that made all the sampling on the object of the Centre Pompidou. And thank you for listening.
Thank you, Eleonora. Your affiliation is the French National Library.
Yes.
That I know very well, because he is one of the few pre-Columbian codex, the Bourbonicus codex.
Yeah, exactly.
You know that there are 13 in Europe, all in Europe, and we have studied by Molab 9 of them, but unfortunately not the Bourbonicus codex, because it was studied by our good friend Bernardo Lavetrin.
Yes.
So I visit and discuss with him. Thank you. You have,
Thank you.
We have time for one question, one comment. Okay, thank you again, Eleonora. Now, the last speaker, but the first on my heart, Francesca Gabrielli. It sounds very strange, odd to me called Francesca, because it was Franceschina for us. I still remember when very young and shy was sitting in the first bench in Via Elce di Sotto, listening to my lecture on inorganic chemistry and to the Brunetti lecture on cultural heritage. The microphone is yours, Franceschina.
Thank you. Okay. Thank you so much, Professor, for the introduction, and all the organizers for inviting me, because it's really an honor for me to be here today. So I will talk a little bit about what I've been doing at the Rijksmuseum in the last 3-4 years, and I will actually point a little bit the attention to the potential of reflectance imaging spectroscopy in a museum environment. But before to do that, I would like to recap a little bit my history. As Professor Scamerotti just said, I graduated in chemistry and physical chemistry at the University of Perugia, and I had the chance to meet Professor Brunetti and Scamerotti, which really communicated all the love and passion for this field, and I actually started my journey with them and Costanza and Francesca Rossi and all beautiful people in Perugia. And I did my PhD there and worked with them for about 6 years, doing a lot of different MOLABs around Europe. I had a chance to analyze many artworks from archaeological sites to Jackson Pollock, as you can see in the picture. And I learned a lot about hardcore spectroscopy, I would say. So really the basic spectroscopy things, but also a lot about the approach, how to approach the analytical study of an object, an art object. And I had my first interaction with conservators, because all the users, MOLAB users, were conservators that were asking very specific questions that we had to answer. So that was a very formative experience. But sadly, after my PhD, I had to move because not a lot of possibilities were opening. And I basically moved to the United States for my postdoctoral fellowship at the National Gallery of Art in Washington, D.C., where I had the privilege of working for 2 years with John Delaney, Catherine Julie. And I have to say that I feel very lucky because I learned a lot about spectral imaging, in particular reflectance imaging spectroscopy, and it was very formative for me. And at the same time, I really could interact more with conservators and curators on a daily basis, trying to understand what were their questions and also their requirements in the analysis of artworks. Then, after Washington, I was lucky to land in Amsterdam at the Rijksmuseum, where I am now part of the team, the scientific team led by Katrien Keune. And in Amsterdam, I basically replicated the system that John has at the National Gallery, so I am now responsible for the reflectance imaging lab and everything that has to do with the reflectance spectroscopy. And I was part of many projects, and I will show today a couple of them, which I think are very important, not just for us as a scientist, but for the museum, for curators and conservators. I just wanted to really recap briefly what is reflectance imaging spectroscopy. We have heard today from Marta and also from Gianluca about this technique. I don't know if the audience is all familiar with it, but to understand a little better what I'm going to tell you later, I think it's good to just have a quick recap. So we are working in a spectral range that goes from the visible to the near IR and deep to the short wavelength IR, where we can actually have information about electronic transition and vibrations of molecules. So we are looking at molecules, so molecular information. And this is a very complementary technique to other, like X-ray fluorescence that gives elemental information and so on. And what we do is very easy, let's say. We shine some light, not too much, to the painting, and we collect the light that is reflected from the materials with imaging spectrometers. One thing that I want to point out is that different wavelengths have a different penetration depth. So when you work in the visible range, you're going to be very sensitive to the surface, so to the material that are on the surface. We talk about 10 to 50 micron, depending on the materials. When you go into the near IR or short wavelength IR, you're penetrating down to the ground. And that's a very, very important information for what is coming next. What do we do with this scanning, with this reflectance imaging spectroscopy output? We actually collect something that we call a 3D data cube. So we have as a X and Y, the coordinates of our painting, and the third dimension in this case is the wavelength, but in the case of the X-ray fluorescence, it's going to be the energy. What do we do with this? We can do mainly two things. One is creating what we call false color images. How do we do this? We slide this cube, and we basically obtain an image per wavelength. And I'm showing you some examples of some of the wavelengths. And then we can basically combine some of those images to create false colors. We know that a normal visible image is made of 3 channels, red, green, and blue. And we can actually pick any of the wavelength image and substitute these 3 into the red and green and blue channel. And what we are going to have is an image that looks like it has colors because materials are responding in a different way to light, so they will appear in a different color. I will explain a little bit better in a second. Another thing that we can do is chemical mapping. We can basically identify one of the some reference spectra that we come end member. And once we know that that spectra is related to a certain molecule or a mixture, we can decide to map those spectra on the surface of the painting through algorithm like the spectral angle mapper. I'm not going to go into detail, but you're always welcome to ask. And I've been basically scanning a lot of painting in these years, but I was very lucky this year because Rijksmuseum hosted an extraordinary exhibition of Johannes Vermeer, who is a Dutch master active in the 17th century, and we were lucky to have on our walls 28 over 37 paintings by Vermeer. And during the exhibition, before and after actually, we had a chance to analyze 12 of these 27 paintings with many, many different analytical tools, imaging and not, and in collaboration with the Mauritshuis and the University of Antwerp. And here are my colleagues. And something that I really I wanted to say before, but I will say now, is that what I found very important at the Rijksmuseum in particular is the collaboration with the conservator. We work together every day, and we look at the painting together, we look at the data together, and whatever I'm showing you today is really the results of a very close collaboration. So this is our masterpiece, The Milkmaid by Vermeer. We, as I said, analyzed with many, many different techniques. And the results, of course, of all the identification of materials and pigments is a puzzle that we have to put together. And reflectance imaging spectroscopy, in particular in the visible range, is really allowing us to map some of those pigments that are mainly in the palette of Vermeer, such as ultramarine blue. Ultramarine blue is not really straightforward to be identified with X-ray fluorescence, for example. So reflectance imaging spectroscopy in this case is very powerful. And ultramarine blue is basically the most used blue by Vermeer, and was a very, very expensive pigment. So it was interesting to see how he was using it. And as you see here in this image, we are mapping the presence of a very blue, pure blue, on the apron of the milkmaid and on the tablecloth. But we can also map the presence of an ultramarine that is mixed with a yellow to achieve a green tone on the tablecloth, for example, or on the sleeve of the milkmaid. And I want to point the attention onto the flesh tone, because Vermeer used ultramarine even on the flesh tone to achieve a shadow, basically, which then will actually change in his career. And we discovered that in later paintings he will change this green tone with a green earth, so actually with a green pigment. But in this case and other paintings, he was using ultramarine mixed with a yellow ochre. And this was a nice the mapping of this kind of pigments. It is important because indeed you can not only identify it, but also see where he's actually using it, so as to understand the technique. Then once we have scanned the painting with the vineyard, so with the visible, we have identified a lot of different pigments. It is important to go look at what is underneath of the surface, and we can do this with the SWIR because we are indeed penetrating deep to the ground. And what we end up with is an image like this. As I said before, this is a false color image in the SWIR, and it's like you are peeling off the layers of the painting on the surface that are transparent to the IR. For example, on the apron, the ultramarine is, of course, transparent to the IR. So what we are seeing, here is the underpaint, and you are seeing here something that looks like very dark, because there must be a pigment underneath that is absorbing the infrared light, resulting in a dark in the image. And we know from X-ray fluorescence that there are not a lot of heavy elements there, so we assume that that's a charcoal black. And this means that he basically built up the painting in the underpaint using a dark underpaint. And you can notice the very coarse brush strokes that are running under the arm and on the sleeve. And he was already defining the dark and the light in the underpaint, which is that's the information that we achieved about his creative process. This was also confirmed spectrally, because as you can see, if you compare two spectra that are coming from the apron, one having the dark underpaint and one without the dark underpaint, you can see how spectrally those two points are different. He does the same thing on the tablecloth. He defines the shadow in the underpaint with a dark paint, which is opposite to what he does in the lighter areas. And this is confirmed with the X-ray fluorescence mapping, where you can see the presence of a lead in the light areas, while there is less lead in the dark areas. And also, it's very interesting, as I said, to always go back to your painting and look at the painting, because what you see with the microscope is actually that under the light, the light blue, there is a white underpaint, while under the darker tablecloth, there is a dark underpaint. You can see it clearly through the cracks. So our scientific investigation was actually confirmed looking at the painting. Important also with the reflectance imaging spectroscopy in the shortwave and IR is to be able to look at changes when they are present. And what we could actually see behind the face of the milkmaid is the presence of an element, a couple of elements. And of course, this was also seen previously in a normal IR reflectography, but the lower spatial resolution didn't allow to really understand what it was. But then, thanks to, again, the collaboration with curators and conservators, we have a theory that this is a jug holder, which actually was present in a dollhouse of the same time, and also in other paintings. So that's the theory that we have. I don't have a pointer, but you can see actually the shape of the jug holder on the right of the milkmaid. And another change that we noticed is on the right of the figure, there is in the visible image something very weird, and when you look at the Zweer false color, you can see that there is a shape, and this is a shape of a basket, of a fire basket, where then there was a little fire inside, and then the laundry was supposed to hang to dry. So we believe that this black blob that you see was actually sketched for the laundry, and then you can clearly see the line, the shape of the basket from the false color. And it is very powerful to have an image like that, because of course you see the two materials reacting differently. You can better separate the two contributions. And this was also confirmed with the macro X-ray fluorescence, where we could actually map the tin. So we know that he sketched that fire basket with probably Latin yellow. Okay, so going from Vermeer to Rembrandt, because I was involved also in another project, a big project that Francesca mentioned this morning. I wanted to show you this parallel, because Vermeer paints very small paintings, while Rembrandt paints very big canvases. So it's challenging for us as a scientist in a museum to be able to provide the same kind of information for such a small painting and in a big painting. So we started a journey in 2019 called Operation Nightwatch. We built a glass house in the museum. You can see here the Nightwatch, and the dimension is a pretty big painting. We spent 2 years researching this painting with many, many different techniques, and these are the photos of all my colleagues involved. And this research was actually done to provide an information on the condition of the painting to help the conservators in understanding whether it was necessary to treat the painting or not. And now I can tell you that yes, the answer is that the painting will be treated, and we are now in the phase of testing the cleaning methods. But I think it's very important to point out that this was done in front of the public, of course, but the main thing is that our research was really a way for the conservators to get to know the painting in a better way. And I want to just show you quickly, this is the imaging setup. We had an imaging frame built around the painting, and the camera was sliding in front of the paintings to acquire our 3D data cube that you saw before. And these are the two cameras that we have at the Rijksmuseum in front of the Night Watch. On the left, the visible Nirayar, on the right, the Zwir. And we also built a special system that was allowing us to focus during scanning, which was the first time that this was done. So not only moving the cameras X and Y, but also in a Z direction. And this is the paper that we published about that. It was a big work for me. We scanned for like 2 to 3 months in the morning, in the night, and we had to scan a lot of different areas and then stitch it together. And this is just to make you understand how big of a plan this was and how big the data set at the end we basically had to deal with, which is still actually something that we're doing. I mean, we're still looking at data. And thanks to the help of Robert Erdman, which is our data scientist, we were able to stitch all those little acquisitions that we made. And this is one is the visible image reconstructed by the with the Vernier camera, and on your right is the false color infrared. And he built a tool for us that we can basically navigate the painting very easily. And here I want to show you an example. I hope, yeah. This is the Zwir false color. I am zooming in basically, and you can see that it's very easy to visualize areas that are abraded because the canvas results blue in the false color. So it's very easy for the conservator to open this image and go look around where they can see the canvas and know that in that area there is an abraded area. So it's important for their conservation treatment. And this was also confirmed spectrally, of course, because we can see the canvas in the spectrum. And this was my last example. I think I'm in time. So I want to thank you all for the attention, and the Vermeer team and the Operation Night Watch team for the work that we do together.
Thank you, Franceschina. I am so happy to see a young students grow up as a brilliant researcher. Now, at the end of the first session, I want to make a comment, which is in a way trivial and sad at the same time. Sad, usually I am optimistic, but I must say that I feel a little sad to see so many scientists with their good education in Italy working in many important museums abroad, since they did not have any opportunity in Italy. It is time and necessary to invert this tendency. We shout these sentences many times, but I think it's time to do something. I consider, of course, very important to have expertise in an international context, but we need to have back in Italy at least part of these scientists that, after their experience in abroad, to preserve our culture, diffuse cultural heritage. Now I became again optimist, which is my normal attitude, due to the high quality of this talk of Italian working abroad. I say the Italian because I consider you, Marika, since you had so many contacts with the Italian scientists, you can be considered an honorary Italian scientist. Thank you. I think that it's time to close this section. Thank you.